In this video, we'll take a look at pressure, temperature, and apply the ideal gas law with key terms that we learned from the last video to determine the mass of air in a standard classroom. And we'll go ahead and get started with pressure. So pressure is defined as force per unit area. And force is commonly expressed in units of newtons. You can also see it expressed in pounds, whereas area is expressed in meters squared, or you can also see it in inches squared, centimeters squared, or other common units. 1 Newton over 1 meter squared is equal to 1 Pascal, which is denoted as PA. And on Earth, the pressure is around 1 atmosphere, or 1 atm. And 1 atm, or 1 atmosphere, is equal to around 101,325 pascals. And because it's such a large number, we'll make it easier on ourselves and express this in kilopascals. So 1 kilopascal is equal to 1,000 pascals, similar to how 1 kilometer is equal to 1,000 meters. So this 1 atmosphere is equal to around 101.3 kilopascals. And pressure can be measured in two ways. You can either measure it as gauge pressure or absolute pressure. And gauge pressure is commonly used when measuring pressures of tires. So if you have some sort of instrument right here, if you're measuring gauge pressure, you're looking at the pressure inside of the perfectly round tire that I drew relative to the surrounding pressure. And to get absolute pressure, you take this gauge pressure and you add back the surrounding pressure. Great, this is it for pressure. Next, we'll take a look at temperature. So temperature is a measurement of the average kinetic energy of the molecules. And we're kind of used to either temperatures in Fahrenheit, so room temperature is around 72 degrees Fahrenheit. You might also see Celsius, so that's around 22 degrees Celsius for room temperature. And there's another scale called Kelvin, which is denoted with a K. And to get to temperatures in Kelvin, we take temperatures in Celsius and add 273.15. And Kelvin is based on the idea that at 0 Kelvin, the molecules are stationary. Next, we'll look at the ideal gas law. So the ideal gas law is PV, or pressure times volume, is equal to nRT, which is number of moles times the universal gas constant times the temperature. And this bar just means per mole. That's not an M. Per mole. And that U is for universal, for the universal gas constant. Now, a slightly different form of the same ideal gas law is a little more useful in most of our thermodynamics problems. So we'll go to this slightly more useful form by taking the number of moles and expressing it in its definition. So the number of moles is equal to the mass over the molar mass. And so we keep the other terms the same. And if we move this molar mass division to the universal gas constant, we get this mass times this gas-specific constant. So this is the gas-specific constant times the temperature. And this is gas-specific because the universal gas constant is the same for all gases, whereas the molar mass is different for each gas. And luckily, we have convenient tables that express these gas-specific constant for different gases. So for example, for air, you'll see that its gas constant is 0.287, whereas for oxygen, it's around 0.26. So we'll remember this gas-specific constant of air for later use. So it's 0.287 kilojoules per kilogram Kelvin. Awesome. Now we can get to the exciting problem. So we'll look at the mass of air in a standard classroom. So if we imagine that a classroom and we approximate it as a box, might be some sort of door, maybe some air conditioning or some leaks in the wall. And so this might not seem like a perfectly controlled system, but we can approximate it as a closed system if we shut the door, we cover up those leaks, and we stop the AC from flowing. And we want it to be a closed system because we're just interested in the mass of air in a given point in time. So we're not looking at how much air is going in and out of the classroom. And with this, because air is an ideal gas at room temperature, we can use the ideal gas law. We'll just rewrite the form that we just derived, and because we're interested in mass, we'll divide both sides by the gas-specific constant times temperature. We'll get this useful form. And we'll look at each of these terms now. So for pressure, because this classroom is just on Earth for now, we'll say the pressure is 1 atmosphere, which we found out earlier was about 101.3 invisible threes, 101.3. Let's make that a little prettier. 101.3 kilopascals. And the volume, I looked it up, the average classroom is around 1,000 square feet and 10 feet tall, which conveniently gives us 10,000 cubic feet. And we need this in meters. So we'll do a quick unit conversion. So 1 foot is about 0.3048 meters. And because we needed this in cubic feet, we'll cube both the numerator and the denominator. And we'll pull out our handy calculator. This is so 0.3048 cubed times 10,000. That gets us about 283.17. 283.17. Now we have meters cubed. Next, we'll look at the meters cubed. Next, we'll look at the gas-specific constant. So we found out earlier that air's gas constant is 0.287 kilojoules per kilogram Kelvin. And for temperature, we know that the temperature in Celsius for regular room temperature is around 22 degrees Celsius, and the temperature in Kelvin is just going to be that 22 plus that 273.15, so we'll get to 295.15 Kelvin. And now we can use all these numbers, 295.15 Kelvin, and we can use all of these numbers to determine that mass in that standard classroom. So the mass is going to be that pressure, so 101.3 kilopascals, times that volume, so 283.17 meters cubed, divided by the gas constant of air, which is 0.287 kilojoules per kilogram Kelvin, multiplied by that room temperature of 295.15 Kelvin. And we'll pull out that handy calculator again. So let's take a look at that calculator, clear it, and we'll do this arithmetic. So 101.3, that pressure times that volume, 283.17 divided by that gas specific constant, 287, and we want to divide by that temperature of the room, 295.15 Kelvin, which gets us to about 338.6. And we'll leave the units to look at in a second. So let's dive into the units. So we have kilopascals in the numerator, and we know that we'll keep that K for right now, and we know that Pascal is equal to Newton over meter squared. And for the numerator, we'll multiply that by the volume of meter cubed right here. So we can multiply all of that by meters cubed, which gets us to a kilonewton meter. And in the denominator, we can go ahead and cancel out these kelvins. And in the denominator, we have a kilojoule over a kilogram. Well, joule is the unit of work, and work is force times distance. So force times distance gives us Newton times meter. So we have this kilonewton meter in the numerator, and we have this kilogram in the denominator. And so putting these units back in to the mass, we have a kilonewton meter on top divided by a fraction of kilonewton meter over a kilogram. And when you divide by a fraction, we multiply it by a reciprocal. So kilonewton meter times a kilogram over kilonewton meter. And this gives us a kilogram. So now we know that the units for this mass is a kilogram. And for those of you that are interested, I went ahead and looked at the mass of a pinto bean. So this mass is 0.0004, 4 is not coming out, 404 kilograms. And to determine how many pinto beans represent the mass of the air in a standard classroom, we'll go ahead and divide our mass of air by the mass of a pinto bean and pull out that calculator again, 0.000404, about 838,000 pinto beans. So 838,000, I think it was 200 pinto beans. So we've concluded that 838,200 pinto beans have the same mass as the mass of air in a standard classroom. Thank you for joining me on this video. I'll see you in the next one.